Okay, so we're going to evaluate the triple integral over q of y dv, where q is bounded by the paraboloid y equals 3x squared plus 3z squared, and y equals 3. Okay, you guys, what do you think you should do first? You got to draw it, right? I mean, and it's got to be a good enough drawing. You don't have to be a super great artist, but it has to be a good enough drawing so that you can identify what's what when you're setting up the integral. All right, so can you guys tell me what kind of paraboloid this looks like? What is it doing? How is it opening? Whoops. How is it opening? Which way is it opening? It's not opening up. It would have to have z by itself and some quantities involving x and y squared for it to be opening up. So the variable that's to the first power, when it's a paraboloid, so it looks like a satellite dish, corresponds with the axis of symmetry. Okay? So the y-axis would be the axis that splits this thing down the middle, which means it's a paraboloid that opens sideways. And since the coefficients are positive here, it opens coinciding to the positive y-axis. To the right, if you set it up the drawing in the usual way. So what I like to do on these is I like to draw the paraboloid first because it's easier, and then I can put in my axes later on. Looks something like that. Okay, and then the origin is right here at the vertex, isn't it? And z goes like this. And then the way I've drawn it, this would have to be y going down the middle of the paraboloid. And then, of course, x is over here like this. And then where do we cut it off at? What gives you the cap of this solid? Y equals 3 is a vertical plane parallel to the xz plane, right? And it's going to cut this thing off, because otherwise the paraboloid would just open forever and ever. By the way, another trace of the paraboloid would be in the xz plane. It might look something like that. Okay. So does everybody see what the solid region that you're integrating over looks like? It's that paraboloid cut off or combined with the plane. It's the interior of that solid that you're integrating over. Okay? All right, well, what that means is you're going to want to go with a differential order. Well, you've got a couple of choices. But you're not going to want z first. Okay? You're going to want, since you have y as a function of x and z, and remember the integrand is y. Since you have y as a function of x and z, you're going to want to integrate with respect to y first. Okay? And then either dz dx or dx dz. But I always go with dz dx if it doesn't matter, because then I'm more familiar with how to set up the outer two limits of integration. I'll discuss that in a minute. So you always come up then with the inner limits first. What would y range from? Thinking of y as a function of x and z, then y would range from, okay, left, the way I've drawn it, from left to right. So the left-hand bound on this vertical line that I've drawn would be what we call h1, and that's a function of x and z. And the right-hand bound here would be h2, again a function of x and z. So what would h1 be? No matter where you draw it, h1 would be the paraboloid, wouldn't it? There you go. So that's it for you. It's 3x squared plus 3z squared. 3x squared plus 3z z squared. That would be the bottom inner limit of integration. Does that make sense to you guys? And what would the right, no matter how you draw this vertical horizontal segment, now keep in mind that this segment's parallel with the y-axis, right? Which is the inner variable of integration. So that's an easy way to remember it. Okay, so what would the right-hand bound then be on this line segment? That's going to be constant, right? 3. So that right-hand bound, in this case, is constant. In other cases, it might be a different function of x and z. So it's 3. Any questions on how to get the inner limits of integration? Does that make sense to you? Okay, now what do we do to get the outer two sets of limits of integrations for the middle integral and the actual outer integral, the last integral? Good. We're going to project the solid region Q onto the plane determined by the outer two variables of integration, x and z in this case. And that's easy enough. So imagine that your eyes are right here on the y-axis, looking straight that way. What object are you going to see? What two-dimensional object are you going to see? A circle. A circle. And by the way, if you think about it, what kind of circle is this going to be? What's the radius going to be? Well, what's the value of y at this, at where this remember this curve right here? This curve right here, this trace really, this vertical trace is the trace you get when you set y equal to 3 and look at the cross section that you get when that plane intersects the paraboloid, y equals 3x squared plus 3z squared. Oh, so what's the equation of that circle then? I think I heard it. Did I hear it? Well, what you could do is plug that 3 in for y, right? And then don't you get 3 equals 3x squared plus 3y squared? Which reduces, if you divide both sides by 3, to just 1 equals x squared plus y squared, or the more familiar, x squared plus y squared equals 1. Oh, so that's a circle of radius 1, isn't it? All right. I've shown you this trick a little bit before. Instead of coming up with the limits of integration, by the way, I said project it, so I'll go ahead and follow through on that. So if I project that down onto the x z plane, then it's a I think I wrote y when I meant z, didn't I? Yeah. Yeah. Let me fix that. Sorry about that. So that's 3z squared. I miscopied that. And it wouldn't have made sense the other way. That's why I caught my mistake, because I knew we were projecting onto the xz plane. Okay. So you project onto the xz plane, and you get the circle of radius 1 in the xz plane, the unit circle in the xz plane. Something like that, right? Okay. So the region that we're integrating over is actually the disk, right? X squared plus z squared is less than or equal to 1. X squared plus y squared, x squared plus z squared, I should have said, equals 1 is actually a circle, right? The disk is given by, so r is given by x squared plus z squared is less than or equal to 1. A subtle difference, but an important difference, right? We're integrating over the entire region. That's what that says. So if you wanted to set up your integral, since you're going to probably switch to polar coordinates anyway, couldn't you just say that the outer region of integration is r, where r is x squared plus z squared is less than or equal to 1? So instead of actually coming up with the upper limits and lower limits of integration for the outer two integrals, you're going to switch to polar anyway, because it's a circle that you're integrating over, right? Well, it's a disk anyway. So you could write it that way. Now, it's not bad practice, however, to actually write those upper and lower limits. And we are after practice right now, so I'll do that here. Okay, so lower limit looks like that, upper limit like that for the inner. And then, okay, I went with the order dz dx, which is analogous to z taking over the role of y, dy dx. So we're going to use a vertical rectangle to help us set this up. So the middle limits of integration then should be the limits on z in terms of x. So this should be a function of x. This middle lower limit, this upper middle limit should be a function of x as well. What do? We solve this. Well, we solve the circle formula for which one? For z. And you get the lower bound is the minus root. So 1 square root of 1 minus x squared. That would be the minus root. And then the upper bound here would be the positive root. Does that make sense to you? So that this limit here would be the lower limit, square root of 1 minus x squared. Upper limit, square root of 1 minus x squared. Negative, positive. Okay? And then what does x range from? Now look at the entire circle, entire disk rather. What does x range from? What was the radius? So is one, so negative 1 here to 1 here. There you go. Okay. Now, would you be in your right mind if you tried to integrate this as is? Yeah, probably not. If you had a lot of free time, yeah. So what I'll do is I'll do the, since we haven't talked about cylindrical coordinates yet, I'll do the inner integral. And then for the outer two integrals, we'll switch to polar, which will make life way, way easier. Okay, so let's do this and then we'll take a break. Just so I have enough room here. Let me move this stuff over. Okay, and we'll continue on with this guy. Okay, so if we evaluate the inner integral, what do we get? Integrate with respect to y, what does that give us? Integral of y with respect to y, we get just y squared over 2. Could I pull that 1/2 out front? 1/2 y squared, y over 2, same thing. Or y squared over 2 rather, same thing. So could I pull out the 1/2, make life easier? Okay. And then I get y squared evaluated from this 3x squared plus 3z squared to 3. And we still have dz dx. And then this is what I meant, you guys. Why write down these upper and lower limits? Let's just write down the disk. That is saying the outer limits of integration, we're integrating over the disk given by x squared plus z squared is less than or equal to 1. Or you could write down the limits of integration. But either way, we're going to switch to polar, and it's not going to matter. I want you to put something down. But this is easier to write down. This is like writing down, oh, the outer, the double integral this reduces to, we're integrating over r, where r is x squared plus z squared is less than or equal to 1. Okay? Does the notation make sense to you? Okay. All right, so then we have a 1/2, and then what does this become? Well, up top we get what? When we plug in the upper limit? 9 minus, 3x squared plus 3z squared. Squared? Is that okay? And then dz dx. Now, we switch to polar. And this picture will come in handy in polar coordinates. But now instead of using a vertical representative rectangle, what do we use? We use a spoke, a representative sector. So let's switch. 1/2. Switch to polar. Now, what does the integrand become in polar? 9 won't change, but minus. Okay, careful here. 3x squared plus 3z squared could be written as 3 times x squared plus z squared, right? And then we're squaring that whole thing, I guess, right? So x squared plus z, so z is taking on the role of y here. So x squared plus z squared would be r squared, okay? There's no reason why you can't do it that way. So then what does this whole mess become? Well, you have to square both the 3 that we factored out, right? It's attached to the x1. So that's, let's write that as a 9 times what? I guess I'm not, yeah, I'll write it down. Oh, 9 times r squared, right? Did everybody buy that so far? Now, what do you put in? What extra factor do you put in when switching to polar? So it becomes r and then dr d theta. And now we need the limits. Oops, went up too high. Okay, so now look at my spoke. What does r range from? R ranges from 0 to just 1, right? And then theta, since we're integrating over the whole disk, you think angularly, theta goes from 0 all the way around, right? 0 to 2 pi. Well, that's not near as bad as it could have been, right? Okay, let's clean it up. We get 1/2 integral 0 to 2 pi. Integral 0 to 1. All right, what does this junk become? Well, first of all, I guess I could factor out a 9, couldn't I? Is that right? Yeah, I could factor out a 9 and make a 9/2 out front. I'm a big advocate of factoring this stuff out, okay? The constants, factor them out, it makes life easier. And then what does this become in here? Just 1 minus r to the 4th. But then you have to distribute r to that, right? So it becomes 1 minus r to the 4th. Does everybody agree with that? Times whole thing times r. So what does that become? As a pirate, what would a pirate say? R minus r to the 5th. Did I do that right? dr d theta? Everybody agree with that? Okay. Now, is it so bad? Now, you can even split up the integral into a product of integrals, right? And again, you're allowed to do that when you can split up the integrand into a function of r, possibly times a function of theta. In this case, there is no function of theta, or just if you consider the function of theta 1, then that's fine. And when the limits of integration are constant, you can split it up into a product of integrals, which, I like to do that as well because it makes the clutter go down. Less clutter, more accurate answers usually. So you end up with what? 9/2 integral 0 to 2 pi, just d theta, right? 1 d theta if you consider the function of theta 1. And then times what? Integral 0 to 1, r minus r to the 5th. So it becomes amazingly easier to do in polar after you clean it up, doesn't it? Okay, so what do we get for this first integral? What's the integral 0 to 2 pi of 1 d theta? Just 2 pi, right? So it'd be 9/2 times 2 pi times, okay, integrate this. What do you get? 1/2 r squared minus 1/6 r to the 6th. Evaluate from 0 to 1. And so that becomes just 9 pi, I guess, out front. And then 1/2 minus 1/6. 1/2 is really 3/6, so 9 pi times, what does that become? 2/6, which is 1/3. So that's really 1/3 or just 3 pi. Pi. All right, let's take a break.